So you remember this slide from several lectures ago? What are they trying to make? Remember what the point of this synthesis was, this particular reaction? The idea was to do a catalytic reaction with something that was chiral as the catalyst to do an oxidation on sulfur to make a single enantiomer of omeprazole. And remember, the idea was that the product, after you've gone through these 3 steps that we showed you before, that the product then comes back and is the catalyst again, and you can do another cycle. So in fact, there's this thing called a catalytic cycle. So that what comes in is a peroxide and a sulfide, and what comes out is an alkoxide and the product that you want, the oxidized product, where an oxygen has been added to that unshared pair, that high HOMO. And so the idea of the chiral oxidizing agent was so you'd get a single enantiomer of the product. But do you remember what happened? Right, it gave racemic material. So what did they do? Do you remember? Pardon me? Yeah, ethyl diisopropylamine they added. These researchers added in 2000, and they found out that that gave a 94% enantiomer excess, but for no obvious reason. Now, it would be great if we knew what the reason for this was. And it turned out that, in fact, this kind of oxidative catalytic reaction to be stereospecific, to give a single enantiomer, was the source of the Nobel Prize in 2001. And if we click on this thing here, we can see, should see, yeah, there we go. So this is the Nobel website, and you can see that Barry Sharpless here got the Nobel Prize in 2001 for his work on chirally catalyzed oxidation reactions. So exactly this reaction. So if anyone can tell us how ethyl diisopropylamine does its trick, who should it be? Barry Sharpless, right? Okay, good. We can put this over here. So you'll need this. Put this in your pocket. And we'll clip this on your tie. There, we're all set.
Thanks, Mike. Well, I'd do anything for my friend Mike because he saved me from publishing errors in JAX at least once, and he's saved a lot of us who were willing to listen to him because he's got a genius for seeing flaws in the beautiful stories that people tell and then they realize that if they're beautiful stories, they're going to be too slick usually, and nature doesn't like things to be too slick. Well, I'm going to just using, I think the next slide should be.
So we need to go. First,
yeah.
we need to do this. Is that it?
Oh, you want to get out?
You have to go back to.
Oh, you have that? Yeah. Okay.
There we go.
Okay.
That one.
Well, this is something which we all possibly manipulate in utero. It's interesting because many things in our body, like heart, can be on left or right, and in mirror image. I assume that means they're mirror image related then. But this is a vein and 2 arteries that has a sheath on it, and it's the umbilical cord of a mammal, and it's got a nice screw axis. You know how we like to pull our hand down a screw axis, and then I have other reasons why I think that I handled it. And then they take it away from you at birth. They cut it and they take it away. It becomes a narcissistically cathected object. And that means you're in trouble because you can never heal that wound. You want to get it back, but you can't heal it. You needed that mirror, that umbilical cord back there when you were born. Anyway, that's why I went crazy trying to do asymmetric synthesis. And now, if you're a chemist, you know, unless you're in deep space, I don't know if they have any carbon atoms out there, but you got to be in a very high vacuum to get them. But this is the way we make organic compounds, right? But we don't really do it this way because we have to live in a condensed phase of the Earth. So these are two, but you put them together, this is a point, then you get a line. It's polyacetylene really, but give me the poetic license of just having it be a line. and I'll take one unit out, and now if I add things across that line, I get into the plane, A and B, or I can add them cis or trans. In a sense, you can make anything this way almost, if you could do it by just surgically adding things. Now we're in the plane, and now the job in the plane, and I've actually drawn a trans disubstituted 2-butene, and it has a shape like this, right? It has a methyl group here, and then hydrogen. So there's open space in these quadrants. And if you look at me coming at you this way, and if I turn around, you see it's going to be, well, you'll see it's going to be a mirror image situation, but I'm flat, so I have no chirality as a starting point. I'm in the plane of flat. So then if I add hydrogen to it, I get nothing interesting. But if I add an atom like oxygen to it, like here, then I pyramidalize. And so I can either add the oxygen from my front and go like that, epoxide, or I can add it from my back and I go like that, and that's the other mirror image compound. That's a really cool way, and it works. You can make epoxides that way, and we have reagents today where you can recognize the front and the back of a flat object that has prochirality like this. And back in the early 70s, we saw this industrial reaction that was nice. You could take vanadium and molybdenum, and you could epoxidize olefins with these things called, well, I don't have darn structure, unfortunately, but it's t-butylhydroperoxide. It's the alcohol group here with a peroxide bond. I think you've already learned that peroxide bonds are weak bonds. They have a low-lying sigma star orbital, and you can attack them on the back side and transfer atoms to make transfer to carbon like a homo of an olefin. So what I noticed in one case that allylic alcohols were very much, seemed to be special. It was just noticed by an English chemist in the 30s that they seemed to react better than just normal alcohols. And so, but nobody had taken any really action on that. And
We're not as fast as some people in getting to this stuff. So we should say that an allylic alcohol is one that has an oxygen on a carbon next to the double bond.
oh yeah.
The OH
Oh, right, I forget. The allylic alcohol, allylic means allylic, you're alpha, one atom away from an olefin. So you could have anything there, nitrogen and oxygen. So you have an OH, like an ethanol, that's an allylic alcohol. If there's this is an allylic alcohol, right, where is it? I'm sorry, I don't have the right structures. This is the allylic alcohol. It would be, if I go back one, I'll show you. Not by going forward.
There's the allylic alcohol, actually.
Yeah, but I got one, like here, this is a carbon, that's a carbon, that's a carbon. If I put an OH group there, that's allylic alcohol. If I have another carbon, it's homoallylic. But it has a handle now, and that handle allows it to grab hold of the vanadium. The vanadium has all these alcohol, these are esters. Imagine that's phosphorus. It is like phosphorus, actually, but it's a yellowish liquid, and it exchanges its ligands like the wind with alcohol. So they come in, they go out. It's a real dance. It's fast. You don't have to worry about that happening. Phosphates, we'd all be dead if that happened. We'd melt. But this is a transition metal. It goes to here. Now, and when I'm in the metal, and I have oxygen here, and then I say, have an arm. You can imagine my arm being a double bond with a pi going like this. And here on my belly, I'm going to have an atom. And this is an atom, like, it should be red, you know. Oxygen's red, but he knows why I don't, except for blood. So you come like this, and you grab it, and it pops off me. I'm the activated thing in the metal, and it goes on to there. That's an epoxide, 3-membered ring. And if I attack it with a backhand, I would get the opposite result in terms of attack on, and that's, that doesn't happen because the geometry of the transition states and the projections of the center, you can't get as close to a center shot on this thing with the backhand. So that's my way of starting to explain. We're going to explain a little bit more. Mike's going to do some acting later, and you'll see a little bit more clearly the topology of the situation. But here, it's cool because you get this template. It's like a mandrel. You grab hold of this oxygen atom, which is proto-oxygen. The metal has lots of empty orbitals. It's a D0 metal. It activates the thing this way. And then the olefin lone pair, the HOMO, attacks the backside, and all this funny business goes on. But there's no mechanism. It's a no mechanism transfer. It's one of these, like you draw a bunch of arrows and everything happens sort of in a smooth way. No ions involved, unlike SN2 chemistry. Okay, slow step is then this step, and then it comes off, and more stuff goes on, it goes around. So that's the trick we played here. The first idea was take advantage of fixing the thing. So once you fix this flat system that you want to make go pop up this way or that way, now you have a chance of doing it because the thing you're transferring from can recognize this kind of situation from that one. But it's part of the same molecule temporarily. In fact, it's a covalent bond right there at this point. Too much. I always say too much. Okay, let's keep going. Then came a great man from Japan. He's now a head professor at Kyoto, Oshima. He was fantastic boiler room producer in titanium, osmium, you name it. I think that was where all the work was done for the Nobel Prize. It was done at MIT, but happened at Stanford just because I was there for a few years. But those early years in your career, when you do your work in the boiler room, are what produce you. Like your personality doesn't change after you're 4 years old, right? Or 3 years old. You're pretty much locked in, unfortunately, in some ways. It's a vanadium system, and we put on this chiral machinery here, and it gave us 80% EE. That means enantiomeric excess was 90% one isomer enantiomer, the right hand say, and 10% the other. And this looks good, but it only works for that one substrate. And all the other types with it, you can have like methyls there or methyl there, and you get nothing. So you have to get everything customized. This ligand is, you got to get the right ligand, and that's what you expect with nature. We're taught by Emil Fischer and the lock and key. Nature is supposed to be very, very touchy about changing her preferences. And that was what we expected. Well, I didn't expect that. I expected that this type of olefin and this type with something, that all these would need a class of catalysts, about 6 shapes of olefins. So that's what my dream was, to get maybe 6 catalysts, because we didn't have the paraphernalia that nature has all around. Well, for years we tried, 10 years we didn't get anything. It was always this game of like almost no reliability. And then when we came to titanium, we've been working with vanadium molybdenum. We came over to titanium and we put in tartaric acid ester one day. This wasn't me, it was Katsuki. He should have gotten a Nobel Prize with me because this was half of this. I picked the right metal at that time and the right system, but he's the one who picked the right ligand. And let's go on to the next. You'll see this is tartaric acid. This is so-called natural. It comes from grapes. It's the cream of tartar. When you protonate it, it becomes tartaric acid. Over here is the unnatural, but there's a plant in Africa, Bahia reticulata, that has about, it's a huge area around the Sahara, so there's maybe more of that so-called unnatural than there is of the natural. You know the story about tartaric acid. That goes way back to Louis Pasteur's discovery of tetrahedrocarbon. I mean, the precursor to it. Grapes, very sexy looking things we always like. Humans seem to like to drink them and eat them and look at them. This is the famous recipe. So that day, Katsuki took tartrate and put it together with, oh, I think I forgot to say something here. Yeah. Just quickly, maybe I don't have it. No, it comes later. Okay. Put the TBHP was the kind of oxidant we'd always been using. There's the titanium, which comes from titanium dioxide or titanium tetrachloride. Everything that's white in this world, all these, that's titanium dioxide. It's the only white pigment anybody ever uses. And so that's titanium dioxide. It's very insoluble, but you can make it into this soluble derivative if you do the right chemistry. And this is the wine acid. We put in diisopropyl tartrate as an ester, and we kept getting 90%, 100%, 95. Every olefin we put in that was an allylic alcohol that had this handle on it gave Katsuki about a week of this, and we were just about dying, you know. He said, I was looking at him, he was looking at me. We didn't believe it, you know. So we had to try to kill this, but it was right. And so it meant that here we had some new principle. We could actually just take one catalyst and get them all, almost to get them all, but there had to be allylic alcohols. So this is a famous recipe discovered, I think, in an October day in 1980 at Stanford. I'd already decided to go back to MIT. I might not have decided to do that if this had happened sooner. We get depressed when our research isn't working. I mean, whether we don't show it or not, it's the only thing that matters really to a real killer research guy who wants to understand what makes nature tick. And whatever else, if that's going well, life is good. Otherwise, nothing's good. So I went back to MIT, which is, I wouldn't have if I'd gotten this about 3 months earlier probably. And here we are, there's Katsuki-san drinking tartaric aqueous. It's about 5% aqueous tartaric acid in wine and champagne. And this is on the porch at the Mud Building, which was where our lab was on the top. And what I want to show here is why Katsuki was so important in a nutshell. This is a really nice little substrate. It has this type of alcohol. It's tri-substituted, but you see the OH here? There's no OH over here. This is a more reactive olefin for the transfer of the oxygen, but it doesn't have the handle. So this one ends up winning by a factor of 200 in this system where the oxidation requires the thing to bind and go intramolecular. And that's nice in its own right, but we got racemate all the time, of course, because we have no face selection. So here, and titanium goes about 10 times faster with tartrate when you add it. This does something to make, every other metal, years before, Oshima had taken vanadium and molybdenum, which were the best for isolated double bonds. But you put tartrate in, it kills them. So my instinct would not have been to put tartrate in again. This is the kind of thing, everything in science, the rules change all the time. You wake up in the morning, you should iterate your favorite desire every morning. It's going to look different to you in the shower. And you can never, atomic bomb was made by theoretical geniuses, but the guys who did it actually found, they had aluminum foil in the source. They kept it on there for about a year or two. Some guy said, I don't think we need this. What about if we take it off? That was the answer. I mean, these guys are like us. They just try this, try that in the lab, right? That's what gets really things done in this world. The theories are important. Nobody would even think about trying it without the theory, but okay, a man in California just won Nobel Prize for mixing pain and wine. That's what they said in the LA Times. It's sort of true. Titanium dioxide and tartaric acid. And there's I like my students to know where the Mother Earth is. And I like things to be cheap. I don't like to be far away from a river that's strong or a power source. Or in this case, this is tartaric acid. It comes on 100-pound bags. This is Spanish tartar. And this is Victor Martin, who's one of the heroes of this chemistry from the Canary Islands. This comes to Pfizer. They make things out of it, but it comes in ships in 100-pound bags. And we still have that in our stocks room somewhere. Here's my daughter celebrating the synthesis of the unnatural sugars by this method. And I got the wrong one, didn't I? I threw out the wrong. Yeah, anyway, you're going to have to interpolate. This is the mirror image of the picture that was taken, I guess, because you see the name over here is backwards. But she's looking at the L sugars. These are the ones we don't make. There's 8 of those, the hexoses. And these are the ones Emil Fischer made in his famous work, about the best chemist who ever lived, except for Van Hoff, who was even better because he did organic stereochemistry and physical chemistry, and I think he was the greatest chemist who ever lived. Van Hoff was. But anyway, Fischer was better than anybody who lived in this century, and in terms of understanding and arguments and rationale of synthesis, and he made all the, a lot of these sugars over here. But this is Tito Simboli. She's a photographer, my wife's friend. This was taken in 1983, was on the cover of Chemistry in Britain, and Hannah was 7, and anyway, Tito was a friend, so she took the picture. And this book, though, is a huge book, which was gotten by Nancy Schrock, who's in charge of the MIT archives and is a book restorer. And Nancy, so here we got Nancy Schrock. We got Tito Simboli, whose husband is Dan McFadden, won the Nobel Prize in Economics 10 years later. And Dick won the Nobel Prize a couple years ago, and I won it in 2001. So the picture is kind of connected. And there's Lewis Carroll, of course, Looking Glass Milk, and Neil Fisher. It's a heavy-duty picture, for me anyway. There's Nexium, and maybe I went too far into the other stuff. But here's the atom, the red atom, that's going to end up being transferred onto the sulfur. Well, Mike told you that the diisopropylamine, what would its role be? I hope I can go to the board now and show you a few things. But this catalyst is exactly the recipe, and it makes billions of dollars a year, this product, right? But the patent Stanford patent is no longer valid. It's run out, even though it hadn't run out when they started, but they didn't believe that this was infringing that patent actually in the beginning, but nobody in universities sues companies. They can't afford to. Stanford couldn't afford to. Should I? Yeah. I don't think there's anything else behind that, is there?
Light on the board. Is that enough?
Yeah, that's plenty, yeah. Oh, yeah, I don't really, that's right, I lose the structure. Why don't we just come down a little bit? Oh, it doesn't, we don't need the structure, I don't think. Well, no, I don't think so. I think they can see. Do you remember the vanadium picture? I'll make it titanium now, but there's this alcohol group, and okay. And on this, we have this peroxide group that's bound, and it's bound datively there. It's got this tertiary butyl group here, and then the alcohol is bound here, and well, it goes sort of down. I'll just try to show some of the stereochemistry, and then underneath, it's coming. It's coming folded like this underneath. So I can't draw very well, but this is supposed to be coming with its lone pairs, its pi bonds, on the back side of this bond. So we're going to do an attack on there, and we'll break this bond. We'll bring the lone pair here in, and we get the epoxide. Now, but the thing about this is patent lawyers can be very creative. Like every field has creative people, and Yale is connected to this fellow Bert Rowland, and he was in Palo Alto at the time at a company, and he had just gotten famous or almost infamous because that patent was really aggressive, this Boyer-Cohen patent. He wrote the Boyer-Cohen patent. He's related to Mike because he got his PhD with Bartlett at Harvard like Mike did. So that's a long time ago. That's a great something relationship. And then comes Weiberg, who's here at Yale. He was at Seattle then, and he took postdoc. He decided he liked chemistry in principle. He was smart, physical organic chemist, but he didn't like the lab. He wasn't any good in the lab, and he didn't like to be there. So he became a patent attorney, and did very well. And he writes great patents, and so when he read our paper, our first paper, we gave him a little communication, and then he got Katsuki and me over to his office, and we interviewed us for about 10 minutes. Next day, we got a patent. Never changed a word of it. And I'll tell you why it's creative, I think. This is the, we're getting ready for the next scene, but I could tell you about that. If we don't make it, it won't matter that much. But here's the main, so this is going to be the oxygen, and they should be red, but we have pink here. So is this one, but that one doesn't transfer. This is the one that transfers. So what Roland said is you got a metal, which can grab things. Now, the things it grabs, you know, could be X, it could be sulfur, or a amine group that could grab. And then he just drew it, I think he drew a carbon with no, it could be any carbon, and it didn't have to have just CH2. And then he drew this, G. And then he drew, yeah, he did draw an oxygen atom here, I guess, that was activated. And so this oxygen, he didn't have generality there. That was specific. That was the only thing that was specific, these two things. So this could be any kind of a lone pair. An olefin is a lone pair. Sulfur has a lone pair. Phosphorus has a lone pair. Nitrogen has a lone pair. And sure enough, when I read that, I said, my God, this gives this idea. So we started doing amino alcohols. All these things work, you know? So this is from Bert Rowland, the patent attorney. He's a co-inventor. He was a co-inventor of those other reactions, but we never wrote any more patents. It's a good thing. Don't waste your time on patents. They'll just not use them until they expire. We made enough to go on a vacation once a year in a car, not too far away. Katsuki and I, you know, we got, people think we got rich. One year we got $20,000 each or something. That was a really sharp maximum from the bag-a-bug, gypsy moth traps, this part lower. But, okay, now to show the transfer, I think maybe it would be nice for us, Mike and I, to show what features have to be over here in these ligands. You see the tartrate has this feature. It grabs the titanium, like out front. Let's try to put it out front here. So the titanium is out here. And down in the back here, you have this ester group. And up in the back over here, you have an ester group. And I can't remember if that's what we plan to do. But out here on the front, it's coming the alcohol, this G group. And there's an oxygen that's hot over here that can be transferred. So Mike's going to put that, I'm going to put that on. And yeah, you're the old, is that okay if you're the old?
It's okay.
Maybe it's better if I'm the olefin. No, okay. I'll be the titanium. So see, I've got this oxygen that wants to go off because it's a weak bond. And I've got to get it over to him. He's the allylic alcohol, but we're going to pretend he doesn't have to bind to me. We're just going to do the straight out attack here. And yeah, it's like that, right? So I'm blocked here, but I'm open in these quadrants.
So you're natural tartaric acid.
Is that right? Well, you're quick. I don't. Okay, so I'm natural? Okay, well, wait a minute. And also, but I'm not like this. I'm like that. You see, I'm a three-dimensional world because I'm tartaric acid. I'm sticking out here. So I'm a chiral object now. My mirror image won't superimpose. But he's that way. He's a trans olefin. And he looks like an Egyptian, like, you know, like, anyway.
You have a double bond here, right?
Yeah.
The question is whether you're going to come on here
Actually,
or
the
right
double,
back.
we don't have this quite right. Can you get an arm down here? Because double bond's here. And
No, the double bond's going this way.
okay, you got to go in that way?
So here, right?
Okay, so, yeah, double bond's going that way, okay.
Okay, good. So you,
And, yeah, that's
your
good.
Get your tartrate on.
Okay, because I could go like, I mean, it's like this, I'm sorry. Yeah, I got to go like that. I could go like that. That's the mirror image. Okay, now I'm coming towards him.
But I want it on my back.
Okay, you want it on your back? Oh, my gosh. I can't do it, see? But now, that's the other, you need the other mirror image for that one. So I come this way,
Okay.
and I can, it says think safety. Oh. So now, and then you have to yeah, if he was a good yoga person, he could parameterize a little better. And now, when you put him that way, he's one enantiomer. If you put him on the other way, that's the other enantiomer. Simple. It's real simple, isn't it? Thanks, Mike. Yeah. We just organized that 10 seconds before we came over, as you can see. We didn't have any red ping pong balls. It's good with Velcro. You can do it with Velcro. We did it once with Velcro red balls. Okay. Now, Yeah, I think we're. Oh no, I'm not back to the screen. Let's leave it alone. This is going to be a little
You
explanation.
can raise it up.
Oh, there's a clean one? Yeah. Now, if you look at the structure of the omeprazole, I won't put all the bells and whistles on. It's a imidazole structure, benzimidazole, which has benzene ring, 2 nitrogens. It's a 5-membered aromatic heterocycle, and so you have double bond and 1 H, and I can't remember what's on the sulfur. Is it aromatic ring or is it a benzyl? It's an aromatic benzyl thing, I think. And you might look at this and say, this doesn't look anything like Bert Rowland's thing there, because where are the anchor points that we need? The group that binds the metal. We have the lone pairs all right. 2 lone pairs, rabbit ears, and if you put oxygen on one side, it's the same story as before. This isn't flat to start with, but now we have these pairs. If you put something here, you get 1 enantiomer. Put something there, you get the other. So the idea was to try to get, and Kagan had done this. He's a fellow who could have won the Nobel Prize. I thought should have, but he's in France, and he had done a lot of great work in asymmetric chemistry, and he took the titanium tartrate catalyst of Katsuki, and he found if you put a little water in it and you did the right things and wished it wasn't as general, but you got a very good asymmetric addition. So titanium was already known to do this, but the feature that's important here is the pKa of this benzimidazole is probably, I looked it up, I think it's below that of an alcohol. So that means it can go on the titanium reversibly. So you see the titanium has alcohols on it, or ligands like this, and this can exchange. So we can have that come off, and this and go on, for this heterocycle. And the benzene rings down here, and now we have something like that, a covalent bond, and we've got the sulfur here, and we also have the alcohol. So there's an equilibrium where you could invoke that. But this is not as easy to probably do as an alcohol. It's more encumbered, and it's probably kinetics are slower for this and off of oxygen for the hydrogen transfers that are needed. So I hypothesize here that what the diisopropyl, what the Hunix base, we call it diisopropyl ethylamine, is doing. This is such a hindered amine that it can't react with anything, but it's good for getting protons. So it can't itself get at the oxygen, which you would worry about. It would make an N oxide, and it can't bind to the titanium anyway. Titanium hates nitrogen. I mean, you can't, if you have an oxygen around, it'll spit it out as fast, make your head spin. I mean, this thing is amazingly hating nitrogen. Titanium, and silicon too, but especially titanium. So it's never going to get involved with titanium. So what's it going to do? Well, remember, when you try to get chemistry going in a system like this, this amine has enough pKa power to pull this proton. And usually you could write a concerted mechanism, like, let me erase some of this and have some room here. Well, I shouldn't erase that. I'll go over here. You got this benzimidazole with a sulfur here, and I'm going to put the hydrogen up here. Whenever you engage compounds in acid-base reactions, you look for the basic sites and the acidic sites. There's the acidic site. You might think that's where the titanium goes, but usually the mechanism for these reactions involves simultaneous loss of this proton and attack here. This is the place you can attack. So you'll be attacking the titanium here, and you're going to get some help from. You're going to get a lot of help from this amine because you can put it someplace. Just take it right off, and you'll have some of that ammonium salt around too a little bit. transiently, and this will help you because you need to move things around. That's why this reaction was not good without that amine. You need to scramble the system and keep it rolling so that the things get on and off. Catalysis often has this, like there's there's always a loop. And if you look at any catalytic cycle, there'll be usually one step that's really bad news until you get it fixed. And that step is where it controls the rate. If you get steady state, the slowest step, this is a real democracy, catalysis. There's no step that's more important than any other. The catalyst goes from each step, the titanium is moving through those cycles. If there's a slow step, there's 99.9% of the titaniums that you need stuck before this one mountain that goes way up like Mount Everest. You got to drop that one down. If you get that one down, the rate goes way up. And if you get them all the same height, you're really rolling. And that's a sacred rule. The turnover limiting step is everything in catalysis. And a lot of times, the turnover limiting step is so high they don't even know there is catalysis. If you can break that, you'll find a world of catalysis that didn't exist before. So that's what I think is exciting about catalysis. It's alive. As long as you have some energy to dissipate, that's life itself. So here's what, then I finished this quickly off. Without any details, you can see what I'm going to do here. It's just that hot oxygen atom that's activated the transfer. This is the handle. That would be the allylic alcohol. So it's a dead ringer for the Katsuki, for the Burt Rowland patent, right? That's what I think. And the amine, yeah, the amine makes sense here too. And I guess that's.
So did that patent apply to this process?
Well, Stanford made a little. They brought over 10 people from research, and they brought over 3 lawyers from AstraZeneca, because Stanford thought maybe they should get something out of this. And I told the story like this, and they pretended it didn't make any sense at all, you know, and it was pretty unsatisfying. Burt Rowland was there. I don't know if he's still alive. He had cancer then, but so we didn't. But they'd already made $6 billion because the catalyst patent was the only extant patent, but it did have this feature in it, and so they were right in the. I think they were right in the face of the patent, but they didn't like that, and you know, Stanford wasn't going to pursue it. Another thing I'd like to mention is they invited me over. This was before this meeting about the patent. I guess I started to notice the old titanium chemistry, and Katsuki and I talked, and we agreed that maybe we should raise our hand. But before that, what happened was I got invited to go to a hotel in Munich, the fanciest hotel, and they put me in this big room up the stairs. They wanted me to say something about right and left-handed medicines, and I had a little 15-minute spot to 1,000 or 1,200 gastroenterologists from Germany alone. And they were doing the story about how important drugs have to be optically pure. And that story doesn't wash too well here. And I didn't realize it when I was going, but I went and I did my part. And it is true that many drugs are toxic in one form and good in the other. And I was able to make those points. But what happens here is, and also they gave me this suite on the top that had a spiral staircase to the bed at the very top, and Madonna had stayed there the week before. That's okay for her. She doesn't have a prostate problem. And, you know, I hated that place. I had to come. They should have had a fire pole so I could get down to the bathroom. Anyway, well, what happens is, as Mike told you, you just look at the facts in that system. And I noticed them just the day I was sitting there in the audience and the press was interviewing us. And I whispered to the guy next to me, and he looked at me and frowned. It was about the weights, all right? I mean, the racemate, 20 milligrams, and the optically pure. And I think the optically pure is substantially more reactive in this case because it gets in better. It's, of course, just a prodrug for the thing. But the thing that was missing from the experiments is the 40 milligrams of racemate, which would give them equivalence against the 1 enantiomer of the 20 milligrams of pure. And that was missing. They doubled and it was just a sore thumb there for me, but I didn't say anything. Nobody asked me, fortunately. Because if they had, I would have said something. I imagine, just, you know, it's the way we are, right, Mike? Mike doesn't. He smiles, but he gets the hard evidence in the middle of your talk. Sometimes he does this, but for me, it's the best thing you can get. If you can get killed by a friend, it's the best way to get killed. Anyway, I'm finished. That's it. Yeah, you're welcome.
We maybe have time for one question or so before we get back to our normal business. Anybody got a question for Professor Sharpless? No, well, thanks again.
You're welcome, and I'll
Have a good trip back.
I'll get that stuff to you through Scott. Okay.
Okay, good.
Yeah.
Oh, that's mine.
Oh, it's yours. I don't have
Here,
anything.
this you. Well, I can give that's Scott's?
Yeah,
I'll give it back to Scott.
Okay. Thanks. So long. Good luck.
Okay, back to our routine now. Yeah, I'll be back there. Yeah, I'll bring it to you. Okay. Oh, he forgot to show this picture. There he is with the royalty of Sweden and his wife and the other Nobel laureates in chemistry. Okay. And he was going to talk about carvone too. He wanted you to smell it. I told him you smelled it, but he had an idea for a novel based on carvone, which he didn't have time to get to. Okay, so we were talking about the conformation of rings, and we talked last time a lot about cyclohexane and how it distorted. Remember that it's not really ideal with the axial bonds parallel to the axis. They spread out a little bit, the ring flattens a little bit to minimize the energy as calculated by molecular mechanics. Now, how about in a 4-membered ring instead of a 6-membered ring? Well, if we look at what molecular mechanics says about the source of strain in this system, you can see that the big contributors are bend. That's what Bayer had already talked about the ring strain, right? Having 90-degree angles is not going to be good. So that's costing 13.5 kilocalories per mole. And torsion, because why is there such high torsional energy, 15 kilocalories per mole almost? What's the source of that? Anybody see? As you go around the ring, everything is exactly eclipsed. Everybody see that? Every carbon-carbon bond is eclipsed, right? So that, in molecular mechanics, sums up to almost 15 kilocalories per mole. Now, how would you try to minimize the energy? Is this probably the lowest energy form, or can you think of changing it so that it'll be lower? Any ideas, Kevin? Yeah, if you make it not exactly eclipsed, if you make it a little bit toward staggered by twisting about the bonds, that'll lower that 15 kilocalories per mole. But can you see what happens if you begin to twist around the bonds? It sharpens the angles even more, from 90 degrees to smaller than 90 degrees. So here's what happens when you do it. The bending energy goes up by 2.5 kilocalories per mole, right? But the torsional energy goes down by 3.5 kilocalories per mole, right? If you don't bend it too far. Okay, and the other things stay pretty much the same. So this is a competition between torsion energy and bending energy. And the minimum is reached with a little bit of bending in order to relieve some of that torsion. Now, how about if you had a 5-membered ring? Now you notice notice the bending energy isn't bad, because as Bayer pointed out, a pentagon, a regular pentagon, has just the right angles, 109.5 degrees about, right? So there's hardly any bending, but there's still a lot of torsion from the eclipsing of the carbons. So what you do, if you run the molecular mechanics program, is to cause bending energy to occur, that is, sharpen the angles a little bit, right? But you get rid of a lot of torsional energy by doing that. And this particular conformation, which you can see how it's bent down at the black carbon 8 there, is sometimes referred to as the envelope conformation of cyclopentane. See how it looks like the fold of the envelope bent down. Okay, so there again is a competition between bending and torsion. Now, like plastic models, molecular mechanics is satisfying because it says not only what the structure should be, but why. What is it that makes the energy the way it is? Okay, so you remember last time we passed around the cyclohexanes, remember how they clicked to go from one form to another? So what's happening? The question is, what's the source of the barrier to the cyclohexane ring flip? So here's the chair cyclohexane, and when the ring starts to flip, remember, first you go toward a boat by bending one of those carbons up, like that. Now, what do you think the source of the energy is that makes this hard to do? Why do you go to a maximum energy as you do this, and then it clicks and it goes down again? Sherwin? The torsion. Now, that's a good point. There are, in fact, two bonds, two butanes that become eclipsed, right? Both of the ones on the right. This one is eclipsed, but also this one is eclipsed. Those four, right? And indeed, that's worth about 7 kilocalories per mole of going uphill. But there's an interesting point. You did this with the models, right? And you felt it click. How do those models, those plastic models, know from torsional energy? You see what I mean? If you take ethane in those models and spin it, it spins completely freely. There's nothing in the model. You could make it. You could make the thing that goes into the tube and the tube a little bit triangular so that as you tried to twist, it would go up in energy and then down again, right? You see how you could do that in a model? But that's not the way those are made. They're cylinders. They rotate freely. So why did the model click? Pardon me? Bending of what? Right, exactly. Look at this. Why does the plastic model click? Because when you're halfway across, it's become, if it were flat, if the whole ring were flat, what would the carbon-carbon-carbon angles be if the ring were flat? Sam? If you in a regular hexagon, what's the angle? Dana? Yeah, you got to be careful holding your hand up, even if it's just to scratch your face. What's the angle in a regular hexagon? 120 degrees. It wants to be 109, so it has to stretch out if it becomes flat. And even when it becomes only partly flat, right? This part of it is flat. This one's out of the plane. But that means in order to have this one in there, this bond gets compressed, right? Because if these angles want to be 109 instead of 120, these are going to move, this one and this one will move closer together. So these are in this form, when it's half planar, these angles are bent out and that angle is bent in. So it's the angle bending which in fact does stress those plastic models, which causes it to click. So it's interesting to be able to look at models or at these calculations of molecules as springs and see why various things occur. So, are molecular mechanics programs useful? Yes, definitely they're useful. Are they true? No. Okay, so we'll go on from there next time.
Plane of flat. So then if I add hydrogen to it, I get nothing interesting. But if I add an atom like oxygen to it, like here, then I parameterize it. So I can either add the oxygen from my front and go like that, epoxide, or I can add it from my back and I go like that, and that's the other mirror image compound. That's a really cool way, and it works. You can make epoxides that way, and we have reagents today where you can recognize the front and the back of a flat object that has prochirality like this. And back in the early 70s, we saw this industrial reaction that was nice. You could take vanadium and molybdenum, and you could epoxidize olefins with these things called, well, I don't have darn structure on it, unfortunately, but it's t-butylhydroperoxide. It's the alcohol group here with a peroxide bond. I think you've already learned that peroxide bonds are weak bonds. They have a low-lying sigma star orbital, and you can attack them on the back side and transfer atoms to make transfer to carbon like a homo of an olefin. So what I noticed in one case that allylic alcohols were very much, seemed to be special. It was just noticed by an English chemist in the 30s that they seemed to react better than just normal alcohols. And so, but nobody had taken any really action on that. And
We're not as fast as some people in getting to this stuff. So we should say that an allylic alcohol is one that has an oxygen. Should see. Yeah, there we go. So this is the Nobel website, and you can see that Barry Sharpless here got the Nobel Prize in 2001 for his work on chirally catalyzed oxidation reaction. So exactly this reaction. So if anyone can tell us how ethyl diisopropylamine does its trick, who should it be? Barry Sharpless, right? Okay, good. We can put this over here. So here, you'll need this. Put this in your pocket. And we'll clip this on your tie. There, we're all set.
thanks, Mike. Well, I'd do anything for my friend Mike because he saved me from publishing errors in JAX at least once, and he's saved a lot of us who were willing to listen to him because he's got a genius for seeing flaws in the beautiful stories that people tell and then they realize that if they're beautiful stories, they're going to be too slick usually, and nature doesn't like things to be too slick. Well, I'm going to just using, I think the next slide should be.
So we need to go. First,
yeah.
we need to do this. Is that it?
Oh, you want to get out?
We have to go back to.
Oh, you have that? Yeah, okay.
There we go.
Okay. Well, this is something which we all possibly manipulate in utero. It's interesting because many things in our body, like heart, can be on left or right, and it mirror image. I assume that means they're mirror image related then. But this is a vein and two arteries that has a sheath on it, and it's the umbilical cord of a mammal, and it's got a nice screw axis. You know how we like to pull our hand down a screw axis, and then I have other reasons why I think that I handled it. And then they take it away from you at birth. They cut it and they take it away. It becomes a narcissistically cathected object. And that means you're in trouble because you can never heal that wound. You want to get it back, but you can't heal it. You needed that mirror, that umbilical cord back there when you were born. Anyway, that's why I went crazy trying to do asymmetric synthesis. And now, if you're a chemist, you know, unless you're in deep space, I don't know if they have any carbon atoms out there, but you got to be in a very high vacuum to get them. But this is the way we make organic compounds, right? But we don't really do it this way because we have to live in a condensed phase of the Earth. So these are two, but you put them together, this is a point, then you get a line. It's polyacetylene really, but give me the poetic license of just having it be a line. And I'll take one unit out, and now if I add things across that line, I get into the plane, A and B, or I can add them cis or trans. In a sense, you can make anything this way almost, if you could do it by just surgically adding things. Now we're in the plane, and now the job in the plane, and I've actually drawn a trans disubstituted 2-butene, and it has a shape like this, right? It has a methyl group here, and then hydrogen. So there's open space in these quadrants. And if you look at me coming at you this way, And if I turn around, you see it's going to be, well, you'll see it's going to be a mirror image situation, but I'm flat, so I have no chirality as a starting point. I'm in the...
So you remember this slide from several lectures ago? What are they trying to make? Remember what the point of this synthesis was, this particular reaction? The idea was to do a catalytic reaction with something that was chiral as the catalyst to do an oxidation on sulfur to make a single enantiomer of omeprazole. And remember, the idea was that the product, after you've gone through these 3 steps that we showed you before, that the product then comes back and is the catalyst again, and you can do another cycle. So in fact, there's this thing called a catalytic cycle. So that what comes in is a peroxide and a sulfide, and what comes out is an alkoxide and the product that you want, the oxidized product, where an oxygen has been added to that unshared pair, that high HOMO. And so the idea of the chiral oxidizing agent was so you'd get a single enantiomer of the product. But do you remember what happened? Right, it gave racemic material. So what did they do? Do you remember? Pardon me? Yeah, ethyl diisopropyl amine they added. These researchers added in 2000, and they found out that that gave a 94% enantiomer excess, but for no obvious reason. Now, it would be great if we knew what the reason for this was. And it turned out that, in fact, this kind of oxidative catalytic reaction to be stereospecific, to give a single enantiomer, was the source of the Nobel Prize in 2001. And if we click on this thing here, we can see...
on the carbon next to the double bond.
Oh, yeah. Oh, right. I forget. The allylic alcohol, allylic means allylic, you're alpha, 1 atom away from an olefin. So you could have anything there, nitrogen, oxygen. So you have an OH like an ethanol. That's an allylic alcohol. If there's this is an allylic alcohol. All right, where is it? I'm sorry, I don't have the right structures. This is the allylic alcohol. It would be, if I go back one, I'll show you. Not by going forward.
There's the allylic alcohol, actually.
Yeah, but I got one, like here, this is a carbon, that's a carbon, that's a carbon. If I put an OH group there, that's allylic alcohol. If I have another carbon, it's homoallylic. But it has a handle now, and that handle allows it to grab hold of the vanadium. The vanadium has all these alcohol, these are esters. Imagine that's phosphorus. It is like phosphorus, actually, but it's a yellowish liquid, and it exchanges its ligands like the wind with alcohol. So they come in, they go out. It's a real dance. It's fast. You don't have to worry about that happening. Phosphates, we'd all be dead if that happened. We'd melt. But this is a transition metal. It goes to here. Now, and when I'm in the metal, and I have oxygen here, and then I say, have an arm. You can imagine my arm being a double bond with the pi going like this. And here on my belly, I'm going to have an atom. And this is an atom, like, it should be red, you know. Oxygen's red, but he knows why I don't, except for blood. So you come like this, and you grab it, and it pops off me. I'm the activated thing on the